Hi everyone. Just to tell you, so that we're going to wait a few minutes till 5 past, as everyone's still sort of coming in, and so just so you know, we'll have an additional 5 minutes until we have our keynote. So, thanks. All right, all right. Welcome everyone. I think we still have some of our friends trickling in, but I'm Chris Erdman. I'm the head of open science at SciLife Lab. It's great to welcome you for a second day here. I think the discussions yesterday were really great, and some great ideas that came from it. today it's interesting. We have sort of an open science theme, and I actually have the pleasure of introducing a friend, and I don't think I've ever introduced her before, but a friend in the open science community that comes to us from the Turing Way, and also OLS, the Open Life Sciences, and the list goes on, and she can introduce all the other things that she works on because it's a lot. But I would like to introduce Malvika Sharan, if you can come up. Yeah, thank you.
Hi, everyone. Good morning, and thank you, Chris, for inviting me. Chris did a good job introducing me because I have 30 minutes to introduce all the things that I do. It's a real privilege to be here and talking to you all. Whether you are an early career researcher, a senior expert practitioner, a policymaker, or working in between different sectors, we all face the same question in this day. How can we adopt data science and AI practices that advance accessible, equitable, and community centered approach? How can we ensure that AI development, deployment, and the impact are driven by the needs and values of the diverse community? The answer, from my perspective, is open science practices, as championed by the Turing Way. As we dive in, I invite you to think about your work, the communities that you belong to, scientifically or in societal aspect, and think about how you can embed interdisciplinary practices through data science and AI. I come from bioinformatics background, and for a long time I saw myself as a bioinformatician. And for a long time I did not engage with other kinds of data science that was happening across different sectors. I didn't think that was needed. And then I joined the Alan Turing Institute, which I will give you a bit of introduction to, which allowed me to think about what is my responsibility as a researcher? How can I ensure that the work that I do is ethical and impact society in a positive way? So a bit of positionality, and that's why Chris said that I'm going to tell you about all the things that I do. I am from India. I come from a northeast of India, from a state called Jharkhand, from a very small town called Ranchi for Indian standard, because the population of Ranchi is 1 million. Um, the Jharkhand word stands for a land full of trees, which is basically what that state is. It's a community which is strongly represented by tribal communities, and my state has had long-standing struggle for representation and statehood only granted 2 decades ago. All of these experiences was at the background of my upbringing. I moved to south of India for my bachelor's in biotechnology. South of India does not speak the same language as north of India, and that's where I started to learn how to speak in English with the people on your day-to-day conversation. It really shaped my perspective into how big the world is and how much to learn, and I wanted to move out of India to learn a bit more about biotechnology, bioinformatics. I moved to Germany, where I did my master's and PhD in bioinformatics, and I got very increasingly involved in open science communities. Um, some of the communities that I have listed on the right side, the Carpentries was one of the first that I was introduced to alongside Bioinformatics Foundation. And over the years, I have been involved in organizations like Software Sustainability Institute. I'm a fellow of Software Sustainability Institute. I was advisor for the NASA Transform to Open Science, along with Chris. Chris was part of Carpentries when I was there. And then I have continued on to work with open science communities, and that has really shaped my career. So the reason why I'm telling you this is that it is very important to engage outside our own context to really understand what kind of work people do, how can we bring in different perspective into our work. I joined European Molecular Biology Laboratory, where I manage a project called BioIT, which was to bring together bioinformaticians from different parts of EMBL, which has 5 different sites, into creating shared resources that they care for and that they want to use and that they want their community members to use. And then I moved to London to join the Alan Turing Institute, where I still work I'm a senior researcher there. My focus are on open research and community building. I lead a team of research community managers, which is a new emerging roles, which I'll also tell you a bit more about. I co-founded OLS, Open Life Science, with some of my colleagues in Open Science, which is a training and mentoring program. And we launched that because we saw lack of representation in science in general. And we wanted to improve visibility of marginalized communities in research, data science, and the careers that we hold. So the Alan Turing Institute is a national institute for data science in the UK. There are three main goals that the institute has set for itself. One is to advance world-class research and apply it to solve national and international global challenges, build skill for the future, and drive an informed public conversation. The last one is about convening different sectors into the conversation of data science. A year and a half ago, we had our new strategy, which is no longer new. Turing 2.0 strategy was launched, where we wanted to reinforce these three goals, taking the position of National Institute to advocate for the community and improve public dialogue. The Turing is supported by our collaborator and partners from different sectors. So on the top layer, you see all the industry partners. We have charities, research organizations, NGOs, funders, and UK government agencies. In 2.0, there are three grand challenges that the Turing invests in. One is the health. How can we apply AI to transform healthcare? Second is environment and sustainability. How can we advocate for climate and biodiversity while ensuring that AI improves our understanding and also makes it sustainable? And defense and security. So protecting the UK and the people and the land we inherit. The part that I am interested in is the core capability and infrastructure teams. This is the part of Turing which are more like a cross theme. So across these three challenges, these are some of the things that we need to care for. One is open source infrastructure, which includes open source software, open data, open access, all kinds of open practices, which is where the Turing way is. Expertise in translation. So we have a product management equivalent called research application management and research community management, the team that I lead, and the skills team. Research software engineering, which includes data science, research engineering, and data wrangling. And finally, fundamental capability in data science and AI, so foundational AI models, and how can we ensure that they are adoptable in different sectors. Saying all of these, my focus is always on the community for the fact that data science is extremely socio-technical. The concept of socio-technical system is how people and technology are intertwined at all level of research and data science. So if you would look at my very simplistic representation of life cycle, you can have an idea, research idea that you would see on the right corner. You have a research idea. You want to tell it to someone else. You go and collaborate with them. You design and plan your research. You go out and collect data, either from public domain or you do experiment and collect new data. You do data processing, data cleaning, data visualization, method selection, statistical analysis. You may actually develop AI models. And then you go and publish it. You make sure that these work that you publish are accessible to the right people. Ensuring that in the future, you might want to come back to this work, or anybody from your community might want to access this work, you preserve your work. And finally, you allow other people to reuse it. It's a very idealistic life cycle, which I would love if it was the case. But as you all know, research does not go this smoothly. We never go from one step to other and to other without going back iteratively and improving our own work. And also, other thing to notice that across all of these stages, we involve people. We don't work alone. Even if you don't know it, there are people involved, which is working in the background. So I should have actually thanked Erica for doing all the work for this conference. And people like her, people in library, people in data management, people who are providing you server infrastructure, all of those are required, even though we don't know it. And of course, your own team members. And also talking about data publishing and access or paper publication and access, there are a lot of things that we publish throughout. A lot of the work that we do not get published, and we do not get credit for a lot of those work. So those are the area that me, along with my team, focus on. So open tools, practices, and platforms enable us to build a system where we can think about socio-technical as a main concept in AI application. Coming to the solution part, why we think open science is important. Open science over the year, in 2016, when we were defining open science, all we talked about was making sure that everything that we publish is accessible. And to this day, in 2022 specifically, UNESCO launched another definition which really expanded. It's not just about accessibility, it's ensuring that people are able to be participant of knowledge production that affects them. So open science is an umbrella term that involves multiple different practices, including open source software, open data, open hardware, citizen science, community building, open notebook, crowdsourcing, and all of that. Anybody might not be applying all of them all together in their work, but they often apply a couple of them, for example, either open access along with open software or open data along with open access. And ideally, we want to think about more than two or three. So open science also allows us to think about equity, combining practices to make sure that the work we do is open by design. Of course, accessibility is very important. So not just publishing things so my friends can access it, but anyone anywhere around the world can access it. So there shouldn't be a price barrier to the knowledge we produce, and there should be no technical barrier. So technical barrier is around reproducibility that I'll touch on. And finally, the work we do should be inclusive for everyone. It should allow anyone to participate and benefit from the scientific achievements. Of course, when we work on computational aspect, we may create a GitHub repository and ensure that anybody who wants to look at it can look at it. It can be a bit harder if you're working in experimental lab. You can't just open your lab to anybody who are not trained. But thinking about what aspect of my work can I open up for people who may not have otherwise chance to inform the work that we do is an important step. Underlying open science is a community framework. This community framework we have adopted from open source movement. So open source defines itself as publishing things that anybody can freely access, reuse, reproduce, and build upon, as well as distribute the work that we do. And research community framework is to allow people to collaborate, peer produce, and sustain the work we do. Open science alone is not enough. It's not enough for us to say, oh, I published it. It has open license, just use it. If you don't describe how you used it, what packages you used, what workflow you designed, what particular context you collected your data in, it is not reproducible. So in computational reproducibility, we talk about if same data is applied to same code, for example, it should always give the same result. You can think about replicability, right? Like you can have a different set of data, but same analysis method. You should be able to replicate a result. And that is probably more relatable also in the experimental context. You may have a very robust technology where you have different sets of analysis and that is applied to the same data and it's always pointing to the same result. And generalizability is something that we can aspire for. So thinking about that, we might be building a technology for my particular experiment, but maybe someone else in different lab might want to reuse it and generalize it and adopt it. Of course, when you're doing your PhD or postdoc, you might not have that much flexibility. Um, but thinking about it is important because we are working and building on someone else's technology. In some ways, we can take responsibility to allow someone else to build on our technology. So you might have seen this. There's more to research than research paper. We all publish article. It's important to ensure that the work that we do can be summarized. But it's a summary. It's an advertisement of the work that we do. More and more publishers are requiring us to share code, share data, as well as executable code, for example, the environment that you're running your own code. So thinking about how can we make sure that anybody who's reading my paper can at least reproduce what I'm talking about. And that's the full replication. It is quite fun. Once you start doing it, it's quite fun. Just getting there is very, very hard. I acknowledge it's a lot of work. When we say go into open science, I need to acknowledge that the amount of labor and time you need to invest in learning those practices is a lot. But there is a high reward as well. Once you learn it, it's very hard to unlearn it. Once you do good science, it's very hard to not do good science. So it's a worth time to invest to learn about these open practices. It's quite fun to work with other people. So going back to again my life cycle, that if we add to all the things that I was talking about alongside openness, the reproducibility, you need to also think about I need to describe all the things that I'm doing in the different ways. So it's possible that you wrote your research proposal and it never was published outside. You might actually want to consider publishing your proposal so someone new who has never written a proposal can look at it and understand what goes into writing a really good proposal. You might want to write about your hypothesis, so you may have pre-registration where you can publish the hypothesis and the method that you want to use. So someone else, if they know that there is an error, they can reach out to you and correct it. But also, if someone else is doing some research like you, because there has always been conversation of I'm afraid of being scooped, pre-registration allows you to own the work because you described it already. So yeah, there are many things I won't be covering here, but I'll tell you how you can learn about all of them, and that is the Turing Way. Turing Way is a community-led project on data science. We are an open source, open collaboration, globally distributed community who are working together to make data science accessible, reproducible, and beneficial for as many people as possible. I call the Turing Way a digital common. Digital common is something where you have, let's say, a resource. So in our case, that's a book. It has a community behind it. In our case, it's an open source, open science community behind it. It has set of norms and practices that allows us to sustain the project as well as benefit the society. That's where we share the best practices. And finally, it allows us to take actions, so the interventions that we are taking as researchers. So I'm going to go through each of these four aspects, and at some point I'll run if my time runs out. So the first is the book. It started as a book on reproducibility. That was the first primary goal of the project, to make reproducibility too easy not to do. It's a moonshot goal we will never reach, but we are trying to get there. A lot of researchers who were already working in open science and reproducibility started to come and describe different practices like licensing, version control, code quality, research environment, data management, and so on. And the more we started to talk about this, the more it was apparent that doing good data science is more than open and reproducible practices. There's a lot that goes into it. So we expanded into 5 guides. Alongside reproducible research, we also wanted to think about project design. How can we ensure that the project that we design is open and reproducible to the degree it's possible? Thinking about communication, we're not really always good communicator. So how can we lean into best practices to make sure that there are resources that we can use to communicate about our work properly? Collaboration is hard. Collaboration is not easy, and people would rather not collaborate with anybody if they had the choice. So, and we want to avoid that. We want to make sure that people have reasons to collaborate, they have guidance to collaborate really well, and moral responsibility as well as ethical responsibility to ensure that collaboration is a really important part of their work. And finally, ethical research. As a computational biologist, ethical research wasn't something that I was properly taught during my university as well as PhD, which I regret. So we also decided to have ethical research where rather than going too deep into ethics, we can describe the basic ethics knowledge that all researchers should know. So for example, how to base your research on human rights framework, how to be activist in your own community, how to ask for better working condition for yourself, and how to make sure that the work that you apply is compliant of the policies. So Kirsty is a founder of the project. Until a few weeks ago, she was my boss, but she has stepped down. and I'm the sole lead from the organization perspective. But she's still an independent advisor, and as an open source, open science community, it is a great thing that you can continue to work with people independent of where they go. Anne-Lee Steele is a committee manager, so if you come to the Turing Way, she's the person who would welcome you and talk to you and onboard you. Ariel Bennett, who was previously a program manager, has just joined me as a senior researcher for Practitioners Hub, which I'll introduce as well. And Lele is our research project manager. These are the faces that are running the project from behind, but there are thousands of people who've worked with us. So we are in our fifth year, more than 5 year now. We have over 350 chapters and 500 really active contributors who have written chapters and examples and case studies from their own work describing what open science, reproducibility, and different aspects of data science looks like to them. We are on GitHub. We were always open from the beginning. And there are things like contributors guideline. There are information that allows you to be part of it. So we want to lower the barrier to be a contributor and user of the Turing Way. The reason for that is that we want to be a global set of best practice. We can't be a global set of best practices if we don't have global community behind it. So if you go to the Turing Way, you might think there are 350 chapters. There's already too much. In fact, it is not. There are a lot of things that are not there in the Turing Way, as well as we need to acknowledge that data science and AI are evolving every single day, and we need to keep this project up to date. We didn't know ChatGPT will explode, and it did. And now we need to learn about how to use it ethically, how to not share our personal data. And people are writing about it. There are information about bias and data missingness, which wasn't something that we were thinking about when we set up our project. So there are a lot of practices that are relevant. So one thing that Kirsty always says that there's everyone who has something to share, and that's the special sauce. It's an open source project. Everyone can freely read, reuse, distribute, do whatever they want. They don't need to tell us as long as you cite us. The project totally belongs to the community. We get a lot of investment from the Turing, and that's really great because a lot of open source projects do not get the investment that they need. And that's probably because of that investment we've been able to sustain ourselves so long. And it's built on open infrastructure. We don't want to reinvent any infrastructure. We want to make sure that we pick from what community is already building, and we can give back whenever we have some features to develop. The project has been accessed all over the world, except for one country. Um, I already talked about a few things up there. There are about 6,000 monthly visitors of the book. The book is being translated by a community in more than 5 different languages because we did realize that it's primarily written in English, and that's not the global language. So our community members, specifically Batul Al-Marzouk, who's leading on this effort, who's translating things in Arabic, but also setting up an infrastructure so other people can translate it. We have collaborated with multiple organizations, and a lot of communities, including public sector, have replicated this model, taking the entire infrastructure that the Turing Way have, but to build their own guides that do not reinvent the practices that the Turing Way is writing, but contextualize it in their own particular sector. A lot of resources that I am using on my talk, including the images, are on Zenodo. Everything is under CC by 4.0, unless it's code, then it's an MIT. We have a Slack channel. We are on Mastodon. I have cut down quite a lot of things like Twitter. We don't use that anymore. But we are trying to be where people are so they can learn about us and be part of us. So community. It's already apparent that we are a community-led project. We apply open leadership principle. Open leadership is a group-oriented leadership model for building open culture of engagement by embedding inclusive, transparent, collaborative, and community-oriented approach. So this is not so much about the practices we share, it's about how do we develop these practices. It comes from Mozilla Open Leadership, where the Turing Way, as well as my nonprofit OLS, has come out from, where we apply 3 principles. Understanding. Anything that we build should be open for understanding by anybody who wants to access it. Sharing. We share things, but people who are accessing it should also be able to share the work that we do. And participation and inclusion, that everything that we design is actually open for participation from the start, not an afterthought. There are some pathways to collaboration for beginners. So, for example, if you are new to the community, you can bring in your lived experience, your diverse perspective from your particular research. You can combine effort with an ongoing project or ongoing issue on GitHub. You can just engage with the community, ask question, respond to someone else's question. You can help us make the community much more participatory. We strongly recognize all kinds of contribution, but we also know that recognition means different thing to different people. So telling us how we can make recognition better and model something that you would like to see in academic research, and how we can co-create the work that we do. Over the period, beyond those initial steps, there are people who have started to form their own group within the community. So, for example, there are people who are working on improving accessibility of AI technology, and they're working on accessibility working group. We have a book dash, which are week-long hackathon where people come in and work with their own organization team to add resources in the Turing way. For example, Esther Plump, who works in TU Delft as a data steward, has worked with us for 4 years with collaboration with TU Delft to put all the research data management approaches that they apply in TU Delft into the Turing way. I already talked about localization. One example that I want to give is environmental data science. Alejandro Coca is leading on that project. Alejandro Coca is creating set of executable notebooks where different codes, different examples from environmental research are given. And for any best practices, he would refer it back to the Turing way. So we call it sister project because it's a very complementary model, which we want to experiment a bit more with. And then organizational advocacy. I already talked about Esther Plom, but Carlos Martinez from eScience Netherlands, Lena Karvovskaya from VU Amsterdam. All the Netherlands people, they are very, very open to work on in a way that we are not reinventing the wheel. And we have infrastructure maintainers. So, for example, Sarah Gibson, Jim, Danny, and Brigitte, they often go back to the communities like Jupyter because we use Jupyter Book, Sphinx, or Mist. So they are connected to the outside community, the resources that we use. We recognize all kinds of contribution. And the reason to do that is first that we do want to recognize people's labor in open science. But second, we also want to model what it looks like to recognize in different ways and not just as simple authorship in a paper. So people have opportunity to fix a bug and they will get recognition to fix a bug. We use a bot called All Contributors Bot that allows us to recognize all kinds of contribution, and you don't need to be working on GitHub for that. But we also have a narrative thing which is called Contributors Record, where people can go and write what they have done. So one of my favorite example is Danny Garside, who is a neuroscientist, and during his postdoc, he was working with us as an infrastructure maintainer as a research engineer. And he could build his profile as research engineer within the Turing way, describe that, apply for his next job where this particular experience was needed, giving an evidence for how he has done it outside his project. And many such examples exist. So thousands of contributors, of course, who have been championing our work. The third part is sharing best practice. We already talked about sharing best practice from the research and data science perspective. We are aiming for different sectors to work with us. But of course, because the resource is primarily written by researchers and data scientists, it often does not become apparent to industry professional or public sector how it's useful for them. So open science also means very different thing to different people. And people often don't know what they don't know. So how would you come to a book and decide what you want to read if you don't know that's what you need? So it requires us to go beyond just this contribution model where people who know what they're doing work with us, which is where I established a project called the Practitioners Hub. Practitioners Hub is a forum for cross-sector knowledge exchange with organization across different sectors who are leading data science initiatives. One of the biggest reasons for that was that we had, of course, thousands of users and hundreds of contributors, but that impact was not enough for funders and policymakers. They didn't see the real value. They still asked me, what is the impact at the organization level? Of course, these individuals were going back to their organization and changing the culture, but that's not what I could write because I was getting an email from people saying, oh, thank you for the Turing wave. We used it in our NSF grant and we got funded. But that wasn't public anywhere. Same for some organizations who I invited to join us in Practitioners Hub and talk about their experiences more openly so other organizations can also see the example for what it looks like to apply data science best practices from the Turing way, but in general with the global community. We got funding from Innovate UK project called Bridge AI, which is a 100 million investment in the UK economy to ensure that small medium enterprises are able to leverage AI in the best way possible. Our initial focus have been on sectors that are generally not seen in AI scene, but they have a lot of data like agriculture and creative media, lots and lots of videos and audios and creative outputs which are not being used in a way that AI can benefit artists, for example. Um, so in our first cohort, I worked with Office of National Statistics, Genomics England, British Antarctic Survey, Digital Catapult, Energy System Catapult, and DigiHall. DigiHall was our only small medium enterprise, and rest of them are quite big from different sectors. And our aim was to work with them to understand how do they apply best practice in a way that benefits their own projects and own community. We have been able to engage with the people who are championing this in their organization already. There is no use to bring people who are skeptics of open science and ask them, how do you apply best practice? So we wanted to highlight the work of people who are already championing this work and get them some credit for the work they do, as well as make it apparent for their community where are the challenges and where the help is needed. We co-created case studies with them and also ensured that they were able to talk to each other. So not just us learning from them, but learning from each other so their knowledge is also transferable across different sectors. So we have a series of case studies, each describing how different organizations have worked with the Turing way or outside the Turing way and how they think best practices can help them. Which these are very interesting set of stories that we did not know earlier because government sector would not write about these things in a blog post, but they were willing to talk to us about it. So we set up our goal after this first pilot cohort that the Practitioners Hub should be recognizing champions. We should be sharing best practices from their perspective, and we should be making sure that the impact and values that they are having can be shared through case studies. A few months ago, we onboarded about 20 companies in the second cohort, and most of them are small, medium enterprises, quite a lot from healthcare excellence. There are about 4 areas that we are focusing now. First, to get companies to think about knowledge that they already have within their organization. Second, to understand how ready they are to adopt AI and in which aspect of their business, in the back end, in the front end, where do they need help. Third, which is the main agenda, how to make them to adopt open source and ethical practices in their business. And finally, roadmap development. We can't achieve a lot in 4 months, but we can leave them with a long-term strategy so they can continue to embed best practices. I will not talk about open source AI definition, but if you love open source, I ask you to check it out. There's a lot of split opinions on where the AI is going and how open source can help us with that. This is the final aspect, action, which is about interventions that we can take. So it's enough to talk about these practices, but what does it look like in practice? So this is where I talk about research infrastructure. This is a specialized set of practices. So I have design this very simplistic view of what an organization or research infrastructure look like. So let's say you have a research. This research has contributors, which are the core team. It has users. It could be the community that you want to serve or someone else who would want to use your work. You would generate data or you would use data. All of these are connected. There are choices and options of tools. Some things that your organization can provide, some things that already exist in public domain. So these 5 aspects are where I can start to think about where are we supporting people. In this support, we need to re-examine research infrastructure. For a very long time, we have only recognized researchers, forgetting all the other roles that exist. These researchers have been actually asked to take on multiple roles without ever getting any recognition for that specialized work that they do. So research infrastructure is defined as physical or digital facilities, resources, experts, and services available towards research for the use of the research community. Research infrastructure roles are people who are providing these expertise and services. There are many research infrastructure roles throughout. So you may have public engagement if you're doing clinical research where you require public engagement. You may have trainers and mentors, social scientists, data wranglers, research community managers, ethicists, designers, policymakers. I'm sure there are other people that I am missing. All of these roles have often been taken by PhDs and postdocs or senior researchers who have to learn all of these things outside their core job, which is fine. We learn and we love, but at some point we start to burn out, and that is not okay. Research software engineering is a great example for where they have tried to solve that. So a lot of researchers become bioinformaticians like me, and then they become even good at coding, and they want to pursue that as their career. And then they have to leave academia because academia doesn't have those kind of role. So research software engineering movement wanted to solve that. They wanted to create these roles for researchers who were really good software engineers and allow them to build career in that direction. We are celebrating actually 12 years of RSC movement. There are a lot of work that has happened, and some examples include the Society of RSC in the UK, the eScience Netherlands Center. I'm sure there are quite a lot in Nordic countries too. At the Turing, Dr. Martin O'Reilly leads a team of over 35 to 40 research engineers, data scientists who are helping with the tool aspects. How can we make sure that the work that we are doing are reproducible and high quality? Ida Mihonic is a senior researcher for research applications, which is a new set of role that we have piloted at the Turing to understand how we can create product management mindset within our research communities. So engaging with the external stakeholder early on, making sure that the contributors are not just the core team members, but also people who may be a local council who might be interested in the work that we do, or a hospital who might want to use an app that we're developing. I am leading research committee management team. Um, I, I call ourselves a bridge builder between the tools and infrastructure that we have with the people who are involved in it. But also, the ultimate role is to make sure that the users can become contributors to the project that they want to use. We have written our practices of working in the last 3 to 4 years in a very long preprint that I invite you to check out, but I will give you a bit of overview of what that is. So why we want to have research committee management? In order to build different communities, we want to make sure that people with diverse ideas can be brought together. What do? We embed open science practices. Essentially, if I don't read all of these, because now I have started to figure out that I have only 10 minutes left. Uh, so we take a lot of practices that we have created in the Turing way and apply that in the real time at the Turing projects. The core skills, if you identify yourself with community management, you love engaging with communities, you love engaging with researchers, you want people to connect with each other, you want to make sure that the work that you're doing are known to people. The strategies that you're developing are long term and not short sighted. You provide accountability to your projects, and you have technical expertise that you bring into the project. The kind of projects that my team members are working on include projects like Turing Roche Strategic Partnership. How can we learn about data missingness and make sure that these missingness can become knowledge for us and create some creative diagnostics? We have AIM RSF project, which is AI for multiple long-term diseases research software facility. We Bridge AI that I briefly mentioned, data-centric engineering, Turing RSS Health Lab, which was a multi-organizational collaboration to inform policies, environment and sustainability, data culture, Emma Karoon, who's another senior researcher in my team, we did a research on professionalizing different kinds of roles beyond research committee management, research engineering. And she's leading on a project called People in Data, which is to connect different people, different communities working in data, irrespective of what their roles are. Just to say, why should we invest in having RCM team? That's if you have never considered having a committee manager, you might want to hire one, but one is not enough because there's always a lot of work to do. We provide network support, make sure that people's career progress in the direction very similar to research engineering. People don't have to leave academia if they want to do committee management. So I'm going to skip that just to show you this one, which is to say that Turing has a lot of projects. We might prefer to talk to just our own collaborators, but we take the responsibility to make sure that the work we do is known beyond our collaborators, and which is where we are supporting our researchers to share their work within the Turing way. So we are trying to diversify these roles. You already saw this image. These diversifying shouldn't be limited to identifying what we do, but naming it, professionalizing it, rewarding it. A lot of practices have been written in the Turing way, and also it's supported by multiple policies. The goal is for us to stop casualization in research. There's a lot of problem in traditional research that we want to move away from, which is where the community is helping. So with that, final words on starting tomorrow, I will be switching to 50% of my time to dedicating to my nonprofit, which is OLS, Open Seats. We're dedicated to building and diversifying leadership. And we have been running a lot of training and mentoring program. We have been collaborating with NASA, which is one of our priorities in the next 3 years to ensure open science is embedded in our ecosystem well. And I will be starting another project, which I hope I can announce in a few days. So with that, I'd finish this, and thank you all for listening and giving me the stage.
I think we do have questions. Time for one question, maybe?
We do have 10 minutes for question.
Yes, okay.
So I wanted to save us some time for discussion. So please ask me questions.
Okay, yeah. So one practice that in particular companies have started doing lately is to not release the source code when they publish papers because they claim it might have some danger for the public if the source code is released. I mean, from most of my colleagues, we think it's just an excuse not to excuse the source code. So how can we, but it could be real reasons. So how could we as a scientific community make sure that it's only used when it's really, really needed?
Are you talking about AlphaFold not releasing code?
Not AlphaFold. That was
Okay.
next.
But they haven't released their code.
ESM3. There are a lot of people doing that.
Yeah.
So and of course that's but AlphaFold 3 was not. It's released now, but in CC by 9. But Alpha Missiles was released with that excuse.
Yes. I mean, I agree with you. It's an excuse. But I want to give two perspectives. One, yes, it's an excuse because they want to identify how to make more money and make their company more sustainable. It is not inherently wrong for them to think about their own sustainability, but it is inherently wrong to not make it clear what their code is doing. If they don't want to make their source code open because they don't want to have it in open source, that's fine. But do they describe how certain work was done? So I think my biggest question would be on reproducibility. On the research side, the good news is that journals are making it mandatory now to publish things like Docker image, where you have your own environment and you have deployed your tool and people can use it. I know it because a few days ago, a colleague of mine who has published a lot of paper and a lot of code was happy that he was spending 1 week of his time just to set this up because this is the right thing to do. So I feel like the question on accountability, how do we hold industries accountable if they are not sharing their information? I think it's the public voice. With the reason why I called AlphaFold, because AlphaFold in the recent version has not released their code. They did release their AlphaFold 1.0 code. The 2.0 code is not released because they're setting up a different company where they want to leverage AlphaFold to design drugs or inform pharmaceutical.
AlphaFold 3 was released 2 days ago.
Oh yes.
And it's but it's CC by non-commercial. and with some
non-commercial.
other restrictions also. So it's, I mean, for academic, it's released 2 days
That's
ago.
great, and I would say that's a success because there was a lot of pressure from research community to do that. So I don't have an answer because you did answer the question.
Yeah.
Yes.
Yeah. Thanks. Great talk. So I was thinking about the overall theme here seems to be very well aligned with what would work in I don't know, a liberal democracy right now, and the world being what it is, democracy is somehow on the it's shrinking globally. So can you sort of get China on board on this, or?
China has a massive open source community, so they are actually one of the highest open source publisher in the commercial sector. They're not open on data, and they have strong regulation on open data. So getting them on board of data would be hard, especially in the healthcare sector. For example, genomics data is protected information for them. But open source, I've had the opportunity to talk to a lot of open source researchers from China who are based in China but also based outside, and they are doing a lot. But I was in the US last week on that same note, and and I was visiting a medical research hospital that has a lot of genomics data, and they have a lot of collaboration with different countries so they can combine genomics data and build better analytics. And they are worried because they don't know what the new government would do to the data sharing. AI regulation in EU is something that people were using to reference to inform US as well as in the UK, which is also questionable. So, I mean, I can't be commenting on politics, but I am worried too. And I think the open source community is strong enough that the open source code aspect will be fine with. I think the open data is going to be a big question. One of the slides I was talking about open source AI definition. Open source AI definition leaves out the responsibility to make clear what kind of data was used in building an AI technology, which is a problem. And I think that problem will continue on for a few years until we reach some sort of decision on what kind of transparency is minimum requirement. Yeah.
Thanks.
Well, thank you, Malvika, and I think we're ready for our next round of talks. So thanks
you.
again for joining us, and we have
Thank you.
a big hand. You can hand it over to you, Petra.
Thank you. So we're in the second session, and my name is Petra Magnusson, and I am the DDLS Research School Director, an assignment that I share with Olof Emanuelsson. And during this session, we will have 2 talks, and we start with Patrick Bryant, and this talk will not be broadcasted, so we thereby say goodbye to the YouTube auditoriums, and the next speaker that will be broadcasted will be around 10:15, 10:20. So Patrick, And again. Great. So then I say welcome back to our YouTube audience. So now I would like to welcome Professor Sven Nylander to present, and he is from the Department of Immunology, Genetics and Pathology at Uppsala University, also my department. And you're also a member of the DDLS expert group in the precision medicine and diagnostics.
Oh, yes.
And you're working on brain tumor, and you are doing patient-specific modeling, for example. And today your title is Reconstructing the Regulatory Programs Underlying the Phenotypic Plasticity of Neurocancer. Please, Sven.
Yeah, thank you. Fairly technical title, of course, and I realized that not everyone in the room is a cancer researcher. However, I do think we all sort of share a passion for what happens when long-standing medical or biological questions meet new data generation capabilities and also abstract thinking. I had a great time at dinner yesterday. I mean, there are so many new good brains now pouring into Sweden with that sort of worldview. So first part of the talk will be on recent work from the lab, making the point that the overall growth and presentation of a brain tumor can be very individual, and the root cause of that has to do with state plasticity of the tumor cells. So it's not all genetics. There is also a highly spatiotemporal aspect to the tumors. Notably, both papers are first authored by the same PhD student, Ida Larsson, who's currently doing her postdoc in the US. The second part of my talk, I will briefly describe a new multidisciplinary research center that we are starting early next year, supported by the Strategic Research Foundation. We just got 60 million Swedish crowns in support for doing so. And the broad topic of this center, which is between Uppsala, Gothenburg, and Linköping, is to gradually move away from things like mouse models, which you see there on the left, into human-only organoid on-chip systems of the brain, also containing vasculature. And we believe that these will have important uses, both in cancer research, so pediatric and adult brain tumor precision medicine, but also in vascular malformation syndromes. A diagnosis of glioblastoma is a fairly unlikely lifetime event, but if you get the diagnosis, your prognosis will be quite poor. Standard of care medicine will offer you surgery, radiation, and chemo, basically, and you see survival curves there to the left, the blue curve showing the effect of the latest addition to standard regimen discovered in 2006. And since then, the therapeutic gains have been marginal. To the right, we see an emerging therapeutic modality based on alternating current that gives you another couple of months. It's called tumor treating fields. So glioblastoma is also called glioblastoma multiforme. It's very heterogeneous when you inspect it in the brain. The pioneer in that field is shown to the upper right, called Hans-Joachim Scherer, killed by a bomb in the Second World War. Before that, he did pioneering work on brain tumors, making the point that these cells engage with the brain in fascinating ways. So they climb on blood vessels, they penetrate through white matter tracts and do other things. And the question is if we can sort of understand what underlies this. And to do so, we need to look at the underlying molecular variation both between patients and within patients. And this slide here is meant to summarize the latest 15 years of brain tumor research. Unfortunately, the laser is not working. But long story short, there is enormous genetic variation between patients. To the upper right, you see examples of drug response curves done by our lab, where we see dramatically different responses that do not correlate really that well with the genetics in this tumor. To the lower left, we see typical research from the last 5 years showing that the tumors contain numerous cellular states and differentiation states that are a bit like a perversion of normal neural development. So some of the tumor cells will think that they are astrocytes, others will think that they are stem cells, and so on. And to the lower right, work from our lab showing that what goes on is highly plastic. So we have been asking if this classical notion of different modes of invasion through the brain is related to the states, and also can we control the cellular states much as you control any technical system such as a Segway or anything. And our conceptual basis for thinking about cell state regulation is basically two things. One is so-called module networks that comes out of statistical learning. And the other theoretical approach we're into is basically control theory. So one of the good things about doing brain tumor research in Uppsala is the fact that we have been collecting, not I, but others have been collecting live patient material since the 1960s onwards. And for instance, one of the most studied cancer cell lines in the world is called U87, and the U is for Uppsala. And we're currently around U6000 something. What my lab has been doing for the last 8 years is to systematically inject cells from patients. Cells from each patient go into a cohort of mice that are siblings, injected at standardized coordinates. And then what we see is that completely depending on the patient, you get different invasion patterns and also survival times. And notably, the anatomical variations that we see are very much in line with the original work by Scherer. When we do statistics on the phenotypes that we observed, it's a longer story, but when you do a PCA on it, it shows that there are mainly 2 axes of phenotypic variation. So one style of tumor is more like a gas that is permeating through the brain and which has affinity for white matter fibers. Another style of growth, which we see along the y-axis, is a condensed tumor with perivascular blobs. You see them as spots there. And there's also a third outlier group that looks a bit like scars, called gliosarcomas. So digging a bit into this, what we did was to select 3 prototype cases for each axis, and did a fairly straightforward single-cell profiling experiment where we grafted cells into mouse brains and then dissolved the brains into single cell and run 10x, and then run matched cell line controls that haven't seen a mouse brain as a reference. And two trends emerged from this. So to the left, we see a comparison between cells grown on plastic, shown in yellow, and cells that are exposed to the mouse brain environment. And I think you can appreciate, so these are our so-called U-maps. So it's an abstract representation of single cell variation. Each spot here is a cell. If 2 points are close, they have similar expression patterns. So broadly, what happens when these cells are exposed to the mouse brain, they start blooming out into different directions. And what we could see when we compared these 2 groups was that we have a separation between the more gas-like growth pattern and the more condensed and perivascular one into 2 different regions of gene expression space. So that led us into trying to understand what drives the position of cells in gene expression space. And for this, we have been developing a particular reverse engineering method called single cell regulatory clustering. It's sort of, one could call it a missing link between clustering and network analysis. It doesn't sort of overinterpret the data as a very rich network. It sort of only forms links where you want them, which is between key regulators of bigger clusters of genes. And based on this work, we got nominations of multiple key genes that were driving the different styles of growth, which we have been pursuing for the last couple of years. And here is one example of one of our favorite targets discovered to date, which is called annexin A1. The upper brain here is tumor cells in black in a mouse brain with an intact annexin A1 locus. In the E panel, you see the corresponding tumor with annexin A1 targeted. So what I think you can appreciate is that although we still have tumor cells, they're much fewer and also better integrated into the brain. And the survival gain here is massive for the mice. Interestingly, the targeting of a single gene like this introduces a massive shift of the different cells in gene expression space. And we have lately been mapping the effects of multiple genes using so-called perturbation sequencing, thanks to support from the DDLS. And we're gradually building a catalog of how to reprogram a brain tumor cell. And the ultimate game here is to sort of suppress invasion and also force cells into more drug-sensitive states, one could say. However, when you sort of you have a dynamic system that exists in multiple gears or states and want to achieve a net therapeutic gain, the question of how to push this system around is a bit subtle. If you are dogmatically believing something like the cancer stem cell hypothesis, the world looks a bit like to the left here, where you have a top state, A, that fills the other cell states by differentiation. And then the logical therapeutic idea would be to let's kill the top cell and we're done. If the world looks like the network to the right, I think there's a mathematical term for this, ergodic or non-ergodic or something like that. What should you be targeting, really? And we started thinking about how to map state transition networks and came up with a particular way of doing this using barcoded cells and gradual sampling of fractions of cells that go into single cell sequencing, which is followed by fitting a mathematical transition model. This model representation is formally, it's a set of linear differential equations. The key parameter is a matrix here that gives us the state transition rates. And you can also view the contents of that matrix as a network, a subway map of state changes. If you sum up the columns of the A matrix, you get the net growth of each state. We found that when we expose cells to various therapies, what you achieve is a redistribution of the states and also changes of specific state rates, which is all great academically, but okay, how to use this? And then the payoff comes when using these control theory formulations of state transitions is that there is a sort of control theory 101 way of stabilizing the system, which has to do with thinking about the eigenvalues of the rate matrix like this. So basically, the matrix A will have eigenvalues. if there are eigenvalues that leave the x-axis, it means that you have some sort of oscillation in the system. If you have eigenvalues in the right half plane, which we do here, it means that the system is going off to infinity. So these cells will grow to infinity. So then the question is, how do we push all the eigenvalues to the left? And that will be our criterion for therapeutic success. And what Ida did was to search her network algorithmically to find minimal modifications of the transition rates in order to stabilize the network. And the prediction was that we should block transitions to state 5, which was an oligodendrocyte-like state. And subsequent research has sort of found ways of doing this. We pre-treat with specific drugs like dasatinib before we give standard treatment, and we get a synergistic effect. And this is all fun. On the other hand, it's quite expensive to run 10x every time you want to build an understanding of how cells from an individual patient transit between states. So let's do something that is more powerful and cheaper. And what we have invented in the lab is a cost-efficient and very effective method for introducing fluorescent tags into marker proteins of choice. So basically using gene editing to introduce mCherry, GFP, or something else C-terminally in frame at selected markers. And here we have an example with stem cell marker SOX2. It's high when the cells are stem-like. You give a differentiation-inducing cue, and the SOX2 level drops. And we have lately been doing this on a large scale, so basically trying to tag 100 proteins in patient-derived cells, and it worked in about a third of the cases. So we now have a coordinate system of about 30 dimensions that we will probe together with the Chemical Biology Consortium Sweden in order to find good reprogramming cues. The second method that we have started exploring is sort of a powerful confocal time-lapse imaging applied to both organoids and, in this case, so-called brain slices. So here the world consists of a coronal section of a mouse brain about 0.5 millimeter thick on an air-liquid interface being filmed over a week of time. So one frame here is 2 hours approximately. And what we do is that we can expose the slices to drugs. So to the upper left, untreated cells, upper middle, treated cells. So I think you can appreciate that the cells stop moving, for instance. And what Madeleine Scheppos in my group recently has invented is an AI that sort of looks at each cell individually and classifies them morphologically over time. And interestingly, we also in this case, we get a bit of a state transition network that we will be able to observe. So concluding, we've built a library of 100 patients with characterized invasion phenotypes in mouse. There is a close relationship between cell state distribution and invasion pattern in glioblastoma. We think that this is a major opportunity for targeting. We found a way to ablate perivascular invasion by targeting annexin A1 as a proof of concept. And we are obsessed about optical methods right now for tracing brain tumor growth. On the new SSF Center, this was a national call that has been running for the last year or so. There was a lot of song and dance about which universities should apply. Our particular constellation consisted of researchers from the Ångström laboratory, Maria Tenje, and also Daniel Aili, a materials expert from Linköping, as well as several molecular medicine researchers from the Rudbeck laboratory, experts in biotechnology and also utilization and patient perspective, as well as two of my favorite mathematicians. The overall goal of this center, which we call CNS times 3, is to build vascularized brain-on-chip models for brain diseases. I'm the scientific director. Petra is the managing director. You have a lot of stuff to do these days. In addition to working on these models, we'll work on data accelerated discovery procedures, and this is where the math comes in. So it's what we have in mind is more like a lab in the loop kind of research. We're currently applying for funds to do this in sort of full bloom, sort of. The last aspect is that we have integrated this platform now with biobank collections, both for adult glioblastoma and also for childhood brain cancer, with all treating research hospitals in the country and also Uppsala Biobank. And initially we'll focus on CNS cancer and also a particular type of congenital vascular syndromes. And there are, of course, other brain diseases, but these are the ones that are most obviously detectable in an organoid format, I would say. And in a later phase, maybe you can do psychiatry, who knows. And that's that. If you have any comments or would like to join the fund, you can email me. And thanks again for the invitation. Thanks.
Thank you very much, Sven, for this brilliant talk. Questions? And I can just say I'm as excited as you are to really run this SSF project together. Olli.
So Sven, really fantastic work. Looks like my voice is still down from yesterday. So there's a lot of other fantastic pictures and the movies and so forth. There's a lot of ways that you could sort of reduce this type of a thing to other types of assays of migration and invasion. Yeah. And how much do you have like knowledge that you gain some insights that you wouldn't have otherwise obtained? Question one, and then a related question: that would this type of an assay predict the in vivo survival of the patients that become a functional diagnostics?
Yeah, I mean that question is spot on, I think, and the benefit of having this collection now is that we can analyze them at multiple levels, from petri dishes to artificial printed grids of blood vessel-like structures, to zebrafish, to organoids, to mice, and then back to the human tissue blocks. Observation is never perfect at all levels. My sort of prediction is that brain tumor researchers in the end will be surprised of how simple the assay can be once you realize what to look for. That's my guess. So I'm leaning towards something that is a bit simpler than a mouse model, but still contains an emulation of blood vessels and also white matter, which are essential. I think a nice thing about the organoid system that we are proposing is that it will contain an emulation of the blood-brain barrier as well, which is very good for therapeutic studies.
So while people are thinking about great questions, I can ask you, Sven, this different type of phenotypic characteristics of the tumor cells that you see when you inject them into the mouse brain.
Yep.
Mouse brain. And you describe that they grow along the blood vessels. Have you looked into how actually the blood vessels themselves are affected by this interaction of the tumor cells?
Yeah. The main observation so far is that glioblastomas with a so-called mesenchymal or wound healing like differentiation, they are pretty good at chewing away on small blood vessels. So you will see tumor cells coming to the vessel and then the vessel retracts like this. We haven't had time to talk to vascular biologists about it. Other tumors are completely silent and leave the vasculature alone. So yeah.
We have time for 6 years to discuss that.
Yeah.
Here I am.
Tack.
Yeah, there's one more, Sven. You're not free yet.
Okay, yeah. dying to get off the stage.
Sorry, Sven. You have a fantastic linear ODE model from which you can get transition rates. I'm just curious, is linear the final solution to this, or would there be any advantage in including non-linearities in modeling the state transitions?
Yeah, I mean, I would sort of expect the underlying system to not be very linear at all. The linear approximation, in a way, only has two strong points. You can live with fairly little data, which we have here, and it comes with this nice theory as well. In the current work, we were doing things like perturbation sequencing and so on. We're trying to include neural networks, which I think you might be interested in for this. Happy to discuss. Yeah.
Okay, if there are no further questions, then we thank you so much, Sven. So I have a bit of announcement because we're now going to have a coffee break, and we will have a little bit of a longer coffee break, and we will have to be back by 11:05. Allergies, those of you who are affected by that, please go to table 2. There you will find your specific food for the coffee. So we'll be back 11:05, but Camilla's talk will not be broadcasted. So again, we will have to say goodbye to the YouTube audience, and we welcome you back 11:30 when we will be broadcasted again. So thank you very much.
So Rosa Ventutormo is someone I first met when I was still at the Wacom Sanger Institute as a group leader, and Rosa was doing fantastic work with Sarah Teichmann's group, dissecting at the single cell level another very sex-specific aspect of biology, right? The interaction between the fetus and the maternal tissue, and that was such a striking example of how powerful single cell biology could be to really dissect biology. So now she's been for quite a few years a group leader at the Sanger Institute, and we welcome her here today to give us a talk. Thank you for coming.
Thank you very much for the nice introduction, and it's a pleasure to be here. So I'm going to talk about how we are mapping the female reproductive system using single-cell technologies, and I on purpose put this reproduction in brackets because when we think about reproduction, we tend to think about infertility, but actually reproductive tissues are more than just fertility. Problems with reproductive tissue, female reproductive tissues, have a huge impact on women's health, and we believe that we need to think about these tissues beyond the impact that it may have on infertility. So, human reproductive tissue, despite the importance for women's health, is still a black box. This is due to main causes, the difficulty of accessing human tissues, the fact that reproductive biology is under-researched. If you do a quick check on the PubMed, there are 4.5 more papers on non-reproductive organs than reproductive organs, and the fact that there is a huge funding gap on women's health. Things seem to be changing, but in the funding space, I cannot see the big change yet. There are multiple differences between humans and mice, meaning that we really need studies on humans. And there is still a lack of complex in vitro models. There are some very simplistic models out there, but some that really comprises the complexity of the tissue is still missing. That really comes despite the importance of reproductive tissues for women's health. Just some numbers with endometriosis, which affect 1 out of 10 women in reproductive age, and it's a very painful disease, or heavy menstrual bleeding affecting 30% of women, in addition to pregnancy complications, around 8% of the pregnancies, and that really affects not only the mother, but also the well-being of the baby. So the way we address and are trying to fill in this gap is by having a cell-centric approach. So cells are the fundamental units of life, and our body is built by more than 37 trillions of them. But for us, in our research, they are also our quantitative unit, and we make things really relate to the cell. So for this, we use single-cell multi-omic technologies to really profile the multiple layers of a cell, from the transcriptome to know about cell identity, to more epigenome to know about cell regulation, or the spatial to understand where cells are and how they communicate with each other. Then we use bioinformatics to really integrate the multiple regulatory layers that we profile, extract biological information, and make predictions. And we also develop methods on that space. And finally, we take on some of these predictions, which we follow up doing in vitro experiments, in a way making perturbations. Our readouts from the perturbations are also single cell in a way that they also get integrated with the initial profiling, and that helps on improving our methods to make better predictions. So, so far, our team, one of the main areas of our team has been focusing on atlasing of the female reproductive tissue across the lifespan. And on purpose, we haven't gone that much into disease because these tissues are super heterogeneous and super dynamic. So if we don't know what's changing because of just the heterogeneity of the tissue, it's difficult to know what's happening in disease. So the reproductive tissue system is really built in the embryo. It's really functionally activated in puberty and changes in pregnancy, and then loses its function in menopause. So we have been looking across generating these atlases across the lifespan. All the data is publicly available, and we have ways for you to interact with them. So please go to this if you're interested. For today's presentation, I'm going to focus on the development of reproductive tissues, and this is a manuscript that is still not peer-reviewed, so I will really appreciate any feedback that you can have. So it turns out that biological sex is a very complex matter because at the very beginning of our lives, we have both the female and the male reproductive system. So what happens is that by default, we became female, which means that these ducts really become organized in these different tissues, the fallopian tubes, the uterus, the cervix, and the vagina, while the male reproductive tract regress. And what happens is that in the presence of testosterone and anti-Mullerian hormone, the opposite happens. So there is a regression of the female ducts, and then the male ducts will become the epididymis, the vas deferens, and the seminal vesicle. And really, the boundaries are finally established postnatally when the tissues will become functional. So it's a very complex, and we need a lot of data to understand what's happening. So with a very talented student in the lab, Valentina Lorenzi, together with a very skilled staff scientist, Cecilia Coresi Maceo, did was to have a huge collection of fetal tissues, and they really extract the female and male reproductive tissues, covering from their emergence to the regression to the differentiation. It was more than 100 samples, and they profiled both the single cell, the attack, and really special data. So this picture here, what it represents, each dot is a cell, and cells cluster based on similarities on their transcriptome. You will see a lot of colors, and these all colors that you see was also our face. We didn't know what they were representing at the beginning. And this was because really there was no references for a single cell data of these tissues because it's poorly understood. And also there were not human cell type markers. And also it was plenty of batch effects. Every sample will comprise different organs depending on the dissection, stage, and sex. So here, what was really crucial for us is to have the spatial data. So in parallel to all the single cell, we also collected different spatial data for more than 23 samples. And what that spatial data means is that you have this H&E, which is what they use in pathology, plus then you can have the transcriptome, which give identity to the cell on top of this, in a way that then you can map back what is the identity to its location. And really, the questions, we use this to really generate the map in a way that then we know, okay, this cell that was here become a fallopian tube or whatever identity, and generating the map. And then once the map is established, we use it to ask two questions. The first one is how sexual dimorphism is established, and the second one is how do male and female reproductive system develop. So because this is a short talk, I'm just going to focus on the female reproductive system development. You can check the bioarchive for more information, and of course, talk to me afterwards if you are interested. So the interest here is that you have such a relatively homogeneous ducts that then become partitioned. And this is what it will happen as well in other systems like the gut, where you have a relatively homogeneous kind of duct and then become really partitioned, and the different organs emerge. So, and here in this case, you see, so it's an homogeneous duct that will give rise to fallopian tube, uterus, cervix, and vagina, which have completely different function. So that poses some challenges on analyzing this data, which was really the single cell data, which was quite discrete clusters, because there is a lack of clear boundaries between the organs, and there is a progressive growth through development. So I'm going to tell you now how we address these challenges in our data, and also the code we developed for this is public, and you can use it for other of your research that also involve this kind of development of an axis. Okay, so here is the tissue. And basically what we did was, with the spatial transcriptomics data, is to build axes. So on one hand, we have this fallopian axis, and this is the spatial transcriptomics. We overlay multiple images to have the full axis. And what we do is that within this axis, we really make it relative between 0 and 2, and that really makes it possible to integrate the different data sets. Likewise, we did the same for the uterus, the uterine vagina axis, and here again we stitch the different images and then we calculate the axis, so everything is relative to this axis. Then we merge the two axes and we have this Mullerian axis, and that really again makes us having everything relative to this axis and integrate the different data. So next, what we did is that usually what people do in single cell is that you have your single cell data, and then you deconvolve the spatial data, assigning spatial coordinates to the cells. But I was very insisting on using the single cell data, because nowadays the single cell data have more unbiased information and have more detail, and has more sequencing depth. So instead, what we did was to transfer these axes to the single cell data in a way that what was a very homogeneous cluster, so if you look towards this UMAP, what was an homogeneous cluster, for example, in the fallopian tube, now becomes, as you can see, different shades of colors, which means that they are organized throughout the axis. So what this allows us to do is to look how gene changes across this axis. And for example, here we have special variable mesenchymal transcription factors, and we did a lot of validations to show that this axis is right, but just on the plot you can see how this is a continuum of expression. And really what that allowed us is to really give for the first time something that was a black box a meaning. And despite we don't have data for this organ, we know that there is some developmental code. So for example, some transcription factors in other organs, such as the limb, that act on contraposition, and we also see them in this organ. And I'm going to show you an example on how we really look at the Hox code. So what happens is that the first cell type to acquire their identity is this mesenchyme. And after they acquire their identity, then they talk to other cells, and the other cells acquire their identity. It was thought that we know what the Hox codes mean in this tissue, where we have HOXA13 for the vagina, HOXA11 for the cervix uterus, and HOXA9 for the fallopian tubes. But when we analyze our data, what we could see, and I cannot point with the laser, but you will need to trust me, that towards the middle is where the fallopian tube finishes. So you can see that for HOXA9, you see some heterogeneity, meaning that this HOXA9 that we thought we knew actually doesn't apply to our tissue. Instead, what we did was to look for the thoracic Hox code, which really patterns other tissues in the body, and we saw that, again, looking at the up to the middle point, that this thoracic Hox code is also patterning this variability within the fallopian tube. And this allows us to establish a dictionary on how Hox code really works in this tissue. So, of course, after the mesenchyme acquire the identity, then it talks to the epithelium, and then they also acquire this identity. And what this allows us is to also look how this dynamic crosstalk happens across these tissues and how the whole identity in the system is established. Again, I won't go into detail, but really going into what are the pathways that are mediating the establishment of the identity of this very complex tube. So I want to finalize to really look more into this diversity between the fallopian tube, which we see that is not that homogeneous. So it turns out that in the adult, we know that there are different functions associated to it. So in the fimbria, which is more towards the ovary, is associated with oocyte pickup, then ampulla is associated with the fertilization, and then isthmus with the sperm capacitation. But first, we don't know, is this functional also have an effect on the transcriptome? Probably yes. And we also don't know, because this is a function for adults, when this patterning is established. The other thing that is interesting from the patterning of the fallopian tube is that it's thought that ovarian cancer emerged from the fallopian tube close to the fimbria, and likely there will be a gradient with that region really expressing some genes that are relevant for ovarian cancer, but yet we don't know. So what our fetal data show, like mapping things across these axes, is that indeed, as you can see here, there is a variability of, and here's in the epithelium, a variability on these regions. And what we found is that in the one close to the ovary, indeed, some ovarian cancer genes emerge, such as PNOC, and there are others that will be useful to study in this ovarian cancer. But of course, you may ask, is this the same gradient that happens in adults or not? So in adults, making what we have done to really map a really long tube, because it's quite long, it's just that it's really fit in a small space because it goes up and down, but it's huge, so we couldn't do it just mapping the whole tube. Instead, what we did was, this is a fallopian tube, and we take the three regions, isthmus, ampulla, and fimbria, and then we correlate changes across our fetal data with the adult data, and we could see a very strong correlation, showing that this function, or this transcriptome that marks the function of the tube later in post-pubertal adult samples, is acquired early in development. And with this, I want to finish on how we have used single-cell technologies and computational technologies to do this cell type mapping, and really understanding something that was a black box, and look at how cells communicate and the identities established. I didn't go into detail, but we have also used this information to study fetal organoids that we use for perturbations, and in particular, we are interested, and we have shown in the paper also some drugs that the mothers can be taken and that can affect the development of the reproductive tracts that we predict from our data and then validate in the in vitro. And we are also interested in using this to prioritize disease-associated variants. And with this, I just want to finish to acknowledge my team, particularly Valentina Lorenzi, Luz Garcia Alonso, and Cecilia y Coresi Maceo, who have been leading this work, and to all collaborators and funders. Thank you.
Thank you very much for that interesting talk. It really illustrated to me how complex it is, the idea to create a tissue atlas, right? And how many dimensions there are before you even start talking about disease. We've got time for a quick question. Yeah, Camilla, you go ahead.
Really nice talk. I'm curious if you have any information of like the mothers of these fetuses, if you have information, for example, if they have like polycystic ovary syndrome, and if that could influence like the way you're seeing.
Yeah, it's a very good question, but we do not have any information about the mothers because it's anonymized data. That's why what we are relying on is on the organoids to do these kind of stimulations and start seeing how that can impact the identity. Because yeah, otherwise it would be impossible. But it's a very pertinent question, so thank you.
One thing that occurred to me from an infection point of view is, of course, that the fallopian tube is also used as an infection model for often very human-specific pathogens like gonococci or chlamydia that infect. And I always considered this a homogeneous tissue, right? So I've just been told, no, it isn't. Do you have any thoughts about using primary tissues then as infection models, or can we do better than that? Can we learn from your work how we can create better models to study infection?
Yeah, no, that's a very good question. So I'm sure we can. I don't know much about infection, but I'm sure that they will affect, and also the immune cells will be different. We are digging more into this regionalization and how different the cells are, especially the immune cells, which will be different in adults. And yes, we can totally learn from this, because the point here is that we have the pathways. Our data show the pathways that are different between the distinct regions. And what we do and what others can do is to then learn from this pathway to modify, because you can modify the media to get a better, a more realistic. So then the current organoids are quite homogeneous within the fallopian tube, and then you can start modeling the different regions by adding the pathways that we predict to be different in the different regions. What you can do is this lab-in-a-loop approach, where you can then also sequence those cells, then compare to your initial data set and see, okay, my modifications on the in vitro are getting the model more realistic or are going far away from this, and this way keep improving the in vitro models.
Yeah, it could be interesting to have a dialogue with our scientists who want to use those models. Yeah. Anyway, thank you very much. Thank you very much, Rosa. This was fantastic. I hand over to Chris Erdmann, who's head of open science for the data center. So thanks, Rosa.
Hi everyone, and we're going to start with a Menti. So take your phones out and go to menti.com, and if you can see the code, it's 8468-6830. And the question to you is, what words do you associate with open science? So this is kind of our collaborative way to tackle this and say, what does open science mean to us? And while you're doing that, I will speak to at least, the behind this talk is to think about, really, think about open science collaboratively. But as I was sort of putting this talk together, I was also thinking about this from a funder perspective too. Like Malvika talked about this from a sort of community perspective. I'm coming at this from a funder perspective of things that you need to know about, as you do your work in open science. So that's great. All right, we have a word cloud. Collaboration, I think this is a strong theme for our meeting actually today. So sharing, accessibility, transparency, open access, all right. Yeah, I mean, I think these are all like really strong parts of open science. So we can move to the slides. Someone mentioned UNESCO right away, so you must have seen my slides ahead of time, maybe, or something like that. But so next, the next slide here, actually, I wanted to compare what we're saying as a community to UNESCO. This open science definition is really where a lot of us are being grounded in how we think about open science. And you can see some of the things that we actually brought up are there. I wanted to see about some of the other things in here that maybe weren't necessarily mentioned in that word cloud, or they were smaller. But the key one I wanted to pull out is this connection with society, right? I think this is one of those areas sometimes that we don't necessarily address right away, and it's important. It's increasingly important these days, and something we should think about. But you can see there, part of this definition is also about making your research more openly available, the collaboration aspect. I think this other aspect of moving beyond the traditional, sort of paper-based way of doing research, and we've seen a lot of that today about sort of more of the dynamic nature of research and how it's changing. Next slide. UNESCO has also put together this great map of all the different things that are under the umbrella of open science. If anyone, this is a pitch to go to the open science room and the open science umbrella to take a picture, but you can see there's a lot under this umbrella of open science, a lot of different sort of aspects to approach. And in many ways, this, in your work, you'll be focusing on particular aspects, like software. We heard software is a really important place for us as far as open source. The other part of this that's helpful is this sort of compass area of the values and principles. And one of the things I wanted to highlight from the funder side is this quality integrity aspect that they, from my experience working with funders, and I neglected to say that I previously worked for Michael J. Fox Foundation and the Aligning Science Across Parkinson's, so work a lot with funders on open science. And so, I think that's a particular area that they're interested in. But I mentioned this is really coming at this from the policies and guidelines, these initiatives, principles to think about. And some of the key ones that you should be thinking about, you probably already have seen some of these, but maybe not. But we have national guidelines in Sweden for open science. You can see the focus area of these guidelines over here, from open access to supporting the infrastructure. We also have this goal of open data by 2026 from the Swedish Research Council. We have our own data policy. I don't know if anyone has looked up our own SciLife Lab data policy, but we have that. And then we have our own initiative that we've joined with 700 institutions around the world, and actually 30 in Sweden, but this coalition to really look at how we evaluate, how we assess research. And a lot of that is around open science. A lot of what Malvika said is what we're looking at SciLife Lab is how do we look at this, through sort of a bigger lens now, like there's more to what's put into the research. And so that, that can include software and the data aspects that we talked about. So the other thing I wanted to show you is that funders are sort of aligning with this as well. You can see across from NIH to Gates Foundation to the European Commission and Wellcome and UKRI. You see there's this general alignment about asking for open access, data sharing, code sharing. We put together this matrix when I was at the Aligning Science Across Parkinson's, and it's a really interesting funder to look at, and actually I think members of our community work with ASAP or MJFF, but it is one of the more forward-thinking funders, and one of the reasons behind that is Sergey Brin believing in open science. One of their funders, he instilled it, and you can see it in a lot of the other funders. They're really starting to look at open science and how they can sort of really move it forward. And then from another side of this is that you see a lot of countries and communities starting to look at how can we show researchers how open science can be shared. And so we heard UNESCO already. UNESCO has an open science monitoring initiative that a lot of us are sort of gravitating around, and that's led by the French. The French have an open science monitoring service to look at how they are sharing their software, how they're sharing their data. The other example I included here is PLOS, the Public Library of Open Science, which is really like another sort of leader in this space, looking at like how can we look at these indicators of how well we're doing in open science in our publications. One aspect of this of sort of sharing your research is to think about FAIR, and I think we heard about this on the first day. So it means findable, accessible, interoperable, and reusable. But really, if you boil it down, it's about making your metadata more machine actionable and more readable. And a lot of that work involves using these identifiers. And some of these you've already seen, some are still kind of developing, but you can see some of the core identifiers over to the right that the community, really whole countries like Australia and Ireland are really sort of, gravitating around and using to facilitate more of this open science awareness. And so, I would say ORCID IDs are probably something you're familiar with in digital object identifiers, but there are other things like RORs for your institution, their institutional identifiers, or RAIDs, which actually help with explaining your research better, the whole project and what's being shared. So I thought this could be a good activity for you to start. How open are you? And I think this is an important question because, again, at the funders, we were starting to ask this question of, well, how open is this researcher? Like, how open, how much do they share as far as open access, their data, and looking at these signals as far as, is this this is a great research to have that's funded in our community, that's collaborative, that shares. So, these are important signals for you to think about. And I don't know if we can pat ourselves on the back a little bit, where we're closing in on the physicists and the astronomers. They have a higher rate of open access sharing. We're more at like 90% in our community, it seems like. I did a little sort of quick estimate of how we were doing. We do share a lot of preprints too, which is great. But obviously there's still work to be done. But we are sharing a great deal already in SciLife Lab. But I would encourage you to go to one of the search interfaces. So like your PMC or PubMed Central. There's other options I list down here. But for yourself to think about, well, how open do I look when sort of people are reviewing and evaluating, looking at my proposals and looking at my research. And one of the things I would encourage you is to think about using your ORCID, building your ORCID profile, and actually in these slides there's a checklist on helping build your digital presence. But that really helps you helps you build that profile and helps signal to these funders as well. And the other thing about FAIR is, a lot of us talk about, my data is FAIR, it's in a database. There's a lot more to FAIR than something like that. And I think one of the things that will be helpful for you, if you haven't, delved into a little bit deeper, is to go to a place like FAIRware and look at how you sort of understand FAIR and how it relates to your research. So I encourage you to go there and look at how aware you are as far as FAIR. And the other side of this that I wanted to sort of bring about is we're also very interested in the data center and generally in SciLife Lab of sort of building this community of looking at how can we make our services, all of our projects more fair. And a lot of this is being built on some of the work that's out there. There's actually an automated tool. There's a number of them that test your services like Fuji. We work with Zenodo on their, they're also trying to look at how they can help researchers be more fair in their data. And then I work with the NIH on the side of giving them guidance with a wider group of like how their repositories can be more fair. And I think a lot of that work will go into our community of thinking like how we can be fair. And my colleague, I don't know where she is right now, but Parul Tawatia is going to help build this fair community of allowing us to talk to each other and learn from each other about how we can get better as far as fair goes. And one of the examples that we recently did was provide some guidance to the pathogens portal in our own group. So, but as far as I just wanted to include one example because open data is one of these sort of focal areas that you see in a lot of these policies. And a lot of the time, what I see is that you know, one of the things we don't understand is we parachute people into our data, so we don't really give them these direct links, these identifiers, or more, you know, just more information on how to access the data and get to it. You know, a lot of the time too, you can also see this data available upon request. That's still pretty common in our community. These are things that, again, the funders are starting to look more at and trying to assess how much of the data are you sharing, you know, how are you sharing it, and they search these data availability statements, or they you know, are searching the data citations as well. But this is the thing I want you to say is, I will not write a statement like this. I think more and more this is going to you know, stand out. It's going to stand out. If you publish your research with something like this, you're going to stand out. And again, it's a signal to funders that, you know, like this may not be someone that we want to fund because of how, you know, if they're sharing their data or being collaborative. So yeah, you're tasked to say this 10 times over. And there's templates out there to help guide you on writing these statements, and I can share this later, or you can access the slides later. But you know, we developed some of these templates with publishers to help researchers sort of understand this. But I think, you know, it's always good to look at a good example, and eLife is one of the best examples as far as how hard they work to make these data availability statements a little bit more complete, and also sort of leveraging these identifiers, but just having a little bit more information for you know, for others to you know, understand your research and reproduce it. And then this is just an example. Actually, it's kind of a helpful example sometimes. So you can put a DOI in this tool, and it will spit back a citation for you. But it's to demonstrate the idea that these identifiers can help pull back all this machine accessible metadata for us to do more on it, right? And this is why you want to provide more metadata, you know, more descriptive metadata, because as we've heard in this meeting, the machines and interaction with machines is becoming more and more important as far as the work that we're doing. And again, you know, look at how discoverable is your data in a system like your PMC. Like, you know, is your data being linked there? And you can interact with the service and say, you know, can I add my links? Can I add my data to this service? To also, again, like, help facilitate when people are sort of looking at your research. So I just wanted to mention, you know, briefly that, you know, it's not just, I'm, you know, part of a big team, and thanks to Ollie, he actually shared a lot of our pictures on an earlier slide, and I don't have to do that. So I can actually focus more on what we do in the data center. And we you know, we can see we do a lot. And I think one of the areas to highlight here is the research data management services, the repository, and you know, the services that we provide with MBIS. Is that we've actually been doing this work around open science for a while, and like, and providing this guidance to all of you. And you know, that's been a service that's been around for a while. I guess from our perspective of growing this open science team, is to think about that, some of the stuff that Malvika mentioned, which is, you know, the community management, and really start, you know, helping facilitate these, you know, the communication between all of our groups in SciLife Lab around open science. And you heard one of those areas around fair metadata. Another one that's exciting, and I'll call out my other colleague here, Sune, who's working on a concept called community of practice, which is something that it comes from other places, but at Michael J. Fox Foundation, we had a community of practice of around data, and it was immensely invaluable to sort of helping the organization think about how we can do better about sharing our data. And so in similar fashion, the community of practice is going to be something that we work with. and learn from Michael J. Fox Foundation about how we can do this with our own community. And then we're going to do something similar to what EMBL has done, which is they have an open science resource. So that's hopefully coming soon in 2025, where we can actually have some of these resources available for you. And then the other thing is, we are doing these events and community events, and one of them was around software recently, where we gathered research software funders. And in our group, at least, there's a lot of interest in sort of facilitating that open source support as well for our community. So that's something we're looking at. And I think it's on to the next, on to the next mentee here. So this is a chance for you, if we switch over, to tell us what types of open science resources, tools, or communities would most support your needs. And this is I thought this was an excellent chance for us to ask you instead of data. All right? A lot of thumbs up already on those. It seems to be all about data right now. Code. Software maintenance. This is great. This is one of these things where you ask for feedback and then you're like overwhelmed because there's all these good ideas from all of you. But I think this will be helpful for us to like think about also other things that we can sort of consider to help all of you, in open science and FAIR. So, but I think that's it. If there's any questions, and you can keep the feedback coming. If there's any questions.
That was a lovely and interesting talk. And so I just wanted to talk about this idea of researchers sort of putting in their statements like that they don't wish to share, and the idea that funders are going to start sort of noticing. I mean, with your work with some of these larger funders like NIH and Michael J. Fox Foundation and so forth, I mean, how much are you finding that is the case? Because there's still a bit, at least in my field, of a sort of data oligarchy where, the big researchers that are doing a lot of the big research, it doesn't seem like the NIH or these other like large institutions are going to stop funding them because they just produce a lot of the big research and their success stories, and these are often, at least in my field, the sort of biggest offenders in terms of statements like that. So do you actually see this sort of data oligarchy sort of toppling, or is it more going to be something that's going to affect younger researchers that won't be able to benefit from the sort of like data hoarding that these researchers above us have been doing? I mean, from your perspective, are they really going to crack down on this?
Yeah, I think there's you saw there was a large umbrella of things to think about, and I find a lot of funders are focused on open access at the moment, but then it comes to data, and you see like probably I would say 50% of them are starting to really they're trying to do more on this front. And the thing is, they're learning from each other. They're sort of, like adopting the same tools. You can see that with the sort of international, efforts that are happening, and then working with publishers, right? So publishers are sort of enforcing this. And having said that, I think we're sort of at a pivot time period where like the culture has been a certain way, and people are sort of, still trying to work this out. I think another thing that I find is sometimes just that the guidance is not clear. Like, what data do you want me to share? And I think that's what we really want to do more, to give you sort of that more concise information about what needs to be shared. But yeah, I think like you're starting to see the numbers go down as far as data availability, because again, people look at that, they see it, right? And the culture starts shifting because you look like an outlier. You look like and it's a signal. It's a signal. And more these systems that I showed you, like for instance, Europe PMC, or there'll be facilities in there now to filter out the research that's where it's like the people that are not sharing. And you don't want to be in that place, where you're sort of not part of the research that is moving forward, and being more progressive. So I don't know if I answered your question, but yeah, I see the numbers going down, and it's just part of this iterative approach, right? Which is like, here's what we're asking for, like here you can see it, it's in the systems now, like people can start seeing like, okay, like, because right now, sometimes it's just not there, it's not shared. And so they can start seeing like, I've done this, and now I can see it's in some of these systems, and actually, a part of the ecosystem, and it's meaning something. And then you sort of circle back again and say, well, we've learned, and let's provide a little bit more guidance, and it's just iterative, right? And so it's going to take time, but already, we are sort of also looking at how we do monitoring, and talking to some of the people doing this work, and they can already take code mentioned and the data and see if it runs, right? They can then sort of automate that as sort of a first test to see like, well, is this a signal that this is a reproducible, article? So, yeah.
So this is a question that's prompted by some of the responses, but also by a very practical case where we ran out of disk quota. Yeah? So we generate large amounts of data, sometimes tens of gigabytes, sometimes hundreds of gigabytes. And the desire is there to have data accessible and everything being reproducible. But then do we have resources where we can store the data? Like, what can we do? Where can we keep it if we run out locally, let's say?
Yeah, well, there's sort of first answer to that question, which is we have resources, right? Like, I think that's one of the things that I've actually had conversations with people on the side, is that, like you have your local university resources, you have some of these national, resources, and some of the resources we have at SciLife Lab, and it's like trying to navigate that is something we help you with. But there are those resources, available, and it's sometimes just not apparent, right? And that's something we help you with. But at least from what I've seen, because one of the hats I've worn is working with publishers, and seeing like that question come up of like, do you want all the raw data? Like, because how are we going to share this? It's not possible. And in those scenarios, that comes back to that question of like, we're still trying to figure out like this space of what needs to be shared, and so some cases it's like what needs to be preserved, like what is needed for that particular research article, versus let's say some of the storage solutions that are out there that that you are using that are temporary, that you can link to, but eventually they will break, right? But as far as your article goes, like there's still at least that immediate access initially, and then you've preserved some of the data that can be associated with that article over time, right? And so, but yeah, as far as storage solutions, this is something you just have, write us an email at Data Center, and I think that's what we're trying to help everyone sort of navigate, as far as the data resources. So, yeah.
Hello, very nice talk, thank you. So I have a question. So basically, what we do, we want to publish benchmarks of models, and they need to be run. Like we need compute as a kind of as a resource, not the data, right? So basically, that would be available for everyone to upload their model and so on, so that someone can benchmark against all available data sets. So how can this be implemented in this type of framework without individual labs paying for compute somewhere else?
That's a good question. I think you know there's obviously some resources that we provide and some that we're sort of testing still. You know, like we work you know with some of the members of our community to sort of understand how we can provide those resources, and I think that's something we would be interested in hearing from you about. You know, like. And so, yeah, we do have those scenarios where we are, like, you know, but it's obviously hasn't, you know, like, in some ways we're trying to also, you know, work with all of you and try and figure out how we can do that together. And so, I mean, that's why, you know, that Menti was there, to see, like, what do you need and how can we sort of help you with that. So, but yeah, again, it's like sort of navigating the resources that are there. That's one step, and then also, you know.
So we can talk to you, right? If like.
Yeah, or my colleagues too,
So
right?
sorry,
Like
yeah.
you've probably seen many of them throughout. You know, like the data center is well represented here. All right. So I'll be followed by Ollie, who has some announcements.
Okay, thanks so much, Chris. So, before I get going with the awards, just a reflection on this session. So first of all, obviously, we are at SciLife Lab a huge supporter of open science, and everybody who has ever get money from SciLife Lab or is a DDLS fellow or is a DDLS student, somebody has signed for you the fact that you should be following these practices, just as a practicality on these things. But let me tell you a little anecdote that when we were planning this meeting, this open science, and obviously thanks Chris for your leadership in these issues and also bringing this on our agenda here today. So there was a lot of discussion then about the open science issues, not just about the data, but the things that were discussed by Arne Elofsson already, which is the AlphaFold. And a funny thing now that I woke up this morning to a bing when the cell phone woke up at 8 a.m. And then I look at that, what's there? AlphaFold 3 source code has been made available. So I think that what the heck is this coincidence that all of a sudden the main discussion topic of the whole meeting solved itself, and there's a message for me at 8 a.m. this morning. Quite amazing. But with that, so let me start this ceremony protocol on Best Poster Award. And I invite Maria, who is representing the Poster Award Committee here, to read the motivation and announcement of the winner.
Thanks, Olli. Yes, so I'm here representing the poster jury again. So that's me, Fredrik Edfors, Björn Forsberg, and Kajsa Torell. And what we did was each one of us independently chose our top 3 posters based on the poster design, the scientific content, and the oral presentation. And then we looked at our overlap. And there was actually quite little overlap in our rankings. And I think that shows just how many good posters we had. But then luckily for us, we had one poster that 3 of us really liked. And that poster really stood out in many ways. I think the first in the design, but I would also like to highlight that we could actually interact with the poster as well and give like immediate feedback, which was quite interesting. So it's my pleasure to announce that the Best Poster Award goes to Virag Varga for the snake poster. And the actual title is Spot BGC, a snake-make pipeline to output metagenomics-derived biosynthetic gene clusters. Yeah, thanks.
So, is that one? Okay, thanks so much for this, and thanks to the poster jury for their work. And now a little bit other thanks as well. Hope you sort of join me now in thanking the people who made this conference really possible. Most importantly, always in SciLife Lab conferences, it's Erika Erkstam and the team of Operations Office that make wonders with this. I'll also now combine Avland, Abhishek, and Chris as the scientific committee members. So let's give an applause to these people. And thank you all for being part of it. I think this was a fantastic meeting. Lots of things happening here, lots of energy in the air. And those of you who are here for the first time, this is how DDLS runs and sort of moves forward. So hang on and sort of see you in this context a year from now again. Now, following this is lunch buffet in the Panorama restaurant downstairs, and that is actually the place where, well, not the place, but in the same level will be the satellite events that happen after that. So thank you, everybody, and enjoy the day and the lunch.